from Kolkata ISI, and recently, I mean, she has been awarded this prestigious Bhatnagar Award, and she solved a long-standing this Jariski cancellation problem in positive characteristics. And a prolific researcher, and of course, a very popular teacher. So we are really pleased to have Professor Neena Gupta today with us, and we are thankful to her for giving lecture for our conference. So I welcome Professor Neena Gupta to start her talk.
Thank you, sir, for this kind introduction. Very good morning to everyone who is a participant here. I'm very happy. It's a matter of real pleasure for me to be a part of this prestigious conference which is being held in KOSM. I have visited KOSM once, so I know it's a very calm and quiet place in Kerala. One should, had it not been a pandemic, we would have visited it again. So today I will talk about a very special kind of threefold of the form x to the power my equal to fx zt. So you can see it's a very special kind of thing. It's a linear polynomial in y, which involves four indeterminates. So why this special, means what is the importance of this? So this special threefold has occurred in various problems in the area of affine algebraic geometry, which includes this affine fibration problem. And at that time, this threefold was studied by T. Asanuma. Oh, there's a typo here, it has to be Asanuma. And then the linearization problem, which again Asanuma studied this kind of threefold. Linearization problem, at this time, Peter Russell and Cora studied this threefold, and Makalimanov solved a problem about this threefold, and that was in 1996. Later, related to Zariski's cancellation problem, I studied this Asanuma's threefold again, and recently in another problem of Mianish's on the ring of invariants of GA action, I again looked at this kind of threefolds. So this threefold being so simple, but it has played a very crucial role in many important problems in affine algebraic geometry. And this list, you can see this seems to be these are very difficult, open, challenging problems still in the area of affine algebraic geometry, and very interesting fundamental problems. In this talk today, we will introduce this problem very briefly. We will not go into the detail of the problem, but we will see how this threefold has emerged as a very important example or as a torch bearing thing for understanding these kind of problems. And later I will present a general theory which I had proved on this threefold, which connects this kind of problems. So connecting all these problems in one theorem, I will present that. And if time permits, I will also discuss about this Mianish's problem on the ring of invariants of GA actions, and how this threefold has played a crucial role there. So throughout my talk, all this notation K will always denote a field. All my rings are commutative rings with unity. For integral domains R contained in B, this notation B equal to Rn denotes the polynomial ring in n variables over R for the elements T1, T2, Tn in B, which are algebraically independent over R. So in other words, this is nothing but the polynomial ring in n variable over R. For a ring R and a prime ideal P of R and an R algebra A, this notation K is round bracket P, this notation denotes the field of fractions of the integral domain R mod P. So if P is a prime ideal, R mod P is an integral domain, then the field of fractions of this integral domain is this field Kp, or in other words, it is also the residue field of the local ring R localized at P. And A tensor Kp denotes the fiber ring of A at P. So in some sense, if you look at a spec of R and a prime ideal P of R, then this is nothing but the fiber ring of the ring A at the point P. Now let me define what was affine fibration problem. So what is a definition? And R algebra A is called an affine fibration, is called an AN fibration if A is flat and finitely generated over R, satisfying that all the fiber rings of A are polynomial rings in n variables over the residue field Kp for every primordial P of R. A very famous, long-standing, open, challenging problem due to Dolgachov and Westphal is that suppose R is a regular local ring of dimension D and A is an AN fibration over R, does it follow that A is isomorphic to the polynomial ring in n variables over R? In other words, this definition says that if you have some kind of the base is a smooth ring, regular local ring with the base is a smooth ring, and the dimension of the base is D, and A is flat. Flat means in some sense there is these fibers vary continuously at every point P of R. So if every fiber is a polynomial ring, can you say globally that A is isomorphic, the fiber is isomorphic to Rn? This is an open problem in general. Few cases have been answered. For instance, the case n equal to 1 has been answered in all dimension by Kambayashi and Miyanishi. So n equal to 1 in some sense is not so difficult. Later, Professor Datta had proved that for n equal to 1, you don't have to assume this hypothesis for every primordial. It is enough to look at only primordials of height less than equal to 2. The case n equal to 2, even for the dimension D equal to 1. So D equal to 1 means R is now a discrete valuation ring. This is a very difficult problem. It was solved by Sathe around 1983 when R contains the field of rational numbers. And this proof is not easy because it requires a huge machinery of this Newton approximate roots, which was developed by General Abhankar and Moe to prove the epimorphism theorem. So this proof is highly non-trivial. Later, Professor Asanuma in 1983, he gave an example that if R does not contain the field of rational numbers, you can construct an A2 fibration over a two-dimensional regular local ring, which is not a polynomial ring over R. In the next slide, I will give you that example. And this problem, as I said, is open even when the dimension of D equal to 2 and N equal to 2. For higher N's and higher D, there is no way we have any clue about this example, about this problem. Now, let me talk about this Asanuma's threefold, which he discovered in 1987 to give a counter example to this question of Dolgachov and Westphal when R does not contain the field of rational numbers. And this is this example. So far, we have no example over a field of characteristic 0. So this is an example. Let K be a field of a characteristic P, which is positive, and A be this threefold, which is defined like this. Here the characteristic of K is P, which is positive, and this integer, this P square, and there is an exponent here, SP, and P is not dividing that S. Let small x denote the image of capital X in A. Professor Asanuma showed that if you invert the small x, then it is clearly a polynomial ring in two variables over the base ring kx 1 upon x. Not only that, for every other primordial of kx, so this includes the primordials which does not contain x, even if P contains x, all those fiber rings are polynomial rings in two variables over the field Kp. Thus, A is an A2 fibration over the ring Kx. And he proved that A is not a polynomial ring in two variables over the ring Kx. Thus, A is an example of a non-trivial A2 fibration over the ring. I think over the ring Kx. So even over a case of in case of a PID, we have an counter example to the A2 fibration problem, and this threefold is now of the same kind of threefold I was describing. Now I will come to this linearization problem. So this was a conjecture due to Kambayashi, who claimed that every algebraic K star action of on the polynomial ring Kn is linearizable. So what is K star? K star is the non-zero elements of the field K. So it's a multiplicative group. So it is this multiplicative group action on the variety spec of variety of this polynomial ring. This is affine n space A and K. So there's a group action multiplicative, which is a reductive group action on this space. And the conjecture is that all such actions are linearizable. Algebraically, it means that if you have a z-graded structure of the ring Kn, if you write it as a graded ring in n z-graded structure, then you can find an homogeneous set of coordinates in the polynomial ring Kn with respect to this z-grading. So this problem, I suppose, is clear. So what about this problem? This problem was known to have an affirmative answer for n less than equal to 2. It's not so difficult. For n equal to 3, this case was proved for the field complex numbers by Russell and Chorus in 1997, and later by Russell and Chorus over any field of characteristic 0. And this initial proof, 1997, this took a long time to arrive, almost a culmination of research devoted to this. About 2 decades of research was devoted to this. Several special cases were proved and published, except one case which they could not handle. And so I will get to the history of this problem in the next slide, next 2 slides. Now, what about in characteristic 0? So characteristic 0, n equal to 3, this is an open problem, yet an open problem. For n equal to 4, this is also an open problem in characteristic 0. N greater than equal to 4, you have non-linearizable K star action when characteristic of K is positive. This was due to Asanuma. I will come to this in the next slide. And for n greater than equal to 5, there also exists non-linearizable K star action when K is a field of real numbers. This was again due to Asanuma, but the problem is still open for the complex number field. So I don't know whether this kind of analogy one can extend it to n greater than equal to 5 in characteristic 0. And there are also results and problems on linearizability of torus action, that is K star R actions, where R is greater than equal to 2, but I will not get into that. Let me first talk about this Asanuma's 1994. What did he do? Asanuma went back again to this threefold, which he has constructed in 1987, to give a counterexample to the A2 fibration problem. It is the same threefold. It's a field of characteristic, positive characteristic, and it is the same threefold. At that time, Asanuma had shown that this ring A is a stably polynomial ring. That means if you adjoin one more variable to this ring A, then it becomes a polynomial ring in 4 variables over K. Using this idea, this ring A, and this statement, Asanuma constructed non-linearizable K star action on Kn for every n greater than equal to 4. However, he was not sure whether A is isomorphic to a polynomial ring in 3 variables over K. Recall that Asanuma had shown that A is not a polynomial ring over Kx, but over K it may still be a polynomial ring, and he left it the problem here itself. Because this he was very much keen to find out, and he knew that if the answer is yes, if A is a polynomial ring in 3 variables, then there would exist non-linearizable K star action on K3 also. So for this dimension 3, this linearizable problem in positive characteristic would have been then completely solved. So he was raised this problem in 1994. Now I come back to this linearization problem in characteristic 0 in over the complex number field about Russell and Chorus. I told you that Russell and Chorus, they were after this linearization problem for more than 2 decades, and in 1992 they have constructed some family of threefolds. Among that, this was one of the simplest threefold, and you can see this threefold is again of the threefold of the type in the title of the stock. So this seems to be a very simple threefold. And what is so important, good thing about this threefold is that this variety V corresponding to this ring A is diffeomorphic to R6. So it's topologically almost C3. This ring A is a unique factorization domain and it's dominated by a C3. In other words, it can be sandwiched between two C3s. And it was an open problem whether this variety is isomorphic to the affine 3 space or is whether A is isomorphic to a polynomial ring in 3 variables over the complex number field. And if the answer is yes, then there would have exist non-linearizable C star actions on C3. But as we know that C star actions on C3 are all linearizable. So this answer is no. And this was proved by McCall-Limonov. So in a breakthrough paper in 1996, McCall-Limonov proved, I think I made a mistake, it is small I. McCall-Limonov proved that A is not a polynomial ring in 3 variables over C. Thus, this paved a way to Kaliman and McCall-Limonov to prove that all the three folds which were defined by Russell and Chorus, none of them is C3. And later, Russell and Chorus completed their proof of the C star actions on C3 are linearizable. So this was a very famous history in the context of a linearization problem, which was based on this threefold. So now I come to this Zariski's cancellation problem. So Zariski's cancellation problem asks whether this polynomial ring in n variable is cancellative over a field K. That is, if A is a ring and if you adjoin a variable to this ring, so if the polynomial ring in one variable over A is isomorphic to the polynomial ring in n plus one variable over a field K, does this necessarily imply that to start with, A was necessarily an isomorphic to a polynomial ring in n variables over the field K? So this was a problem, and this problem was known to have an affirmative answer for the case n equal to 1, and this is answer is yes. And in fact, this case n equal to 1 is an easy exercise. It could have been an easy exercise for an first year undergraduate student or maybe an MSc student. They can prove it using some valuation theory. I said it after Abhyankar, Ikin, and Heinzer. Abhyankar, Ikin, and Heinzer's, their result was much more general. In fact, they proved that whenever R is an unique factorization domain and A is an R algebra, then if the polynomial ring in m variables over A is isomorphic to a polynomial ring in m plus 1 variable over R, then you can say that A is isomorphic to a polynomial ring in one variable over R. So this was a more general result which was proved by Abhyankar, Ikin, and Heinzer. And from this, you can prove this Zariski's cancellation problem. You can deduce, but one need not prove this whole thing for deducing this. One can deduce that for R is equal to Kx, this result for n equal to 1. What about n equal to 2? N equal to 2 requires a good amount deal of research. And in fact, the famous Indian mathematician C.P. Ramanujam was, after solving this problem n equal to 2, in his attempt to solve this problem for n equal to 2, he gave a beautiful topological characterization of the affine 2 space, which is still useful and remembered. Later, Miyanishi gave an algebraic characterization and finally, Miyanishi, Sugi, and with an important contribution due to Fujita, they proved this result in characteristic 0 for n equal to 2. And soon Peter Russell extended their techniques over any perfect field. Recently, we have proved it for any field, irrespective of the characteristic. For n greater than equal to 3, I showed that this Zariski's cancellation problem does not have an affirmative solution in positive characteristic. So I first dealt with the case n equal to 3, where I have considered this asynchronous threefold, which I have described in the first slide. I will go back to in this. And in characteristic 0, this is still an open problem. No one doesn't know any answer to this question. So now let me talk about this solution for n equal to 3. So I went back to this asynchronous threefold, which was there from in 1987. So this A is this threefold, characteristic of K is P, and Asanuma had shown that if you adjoin one more variable to A, it becomes a polynomial ring in 4 variables over K. And he showed that A is not a polynomial ring over the subring Kx. However, he raised this question in 1994 whether A is isomorphic to the polynomial ring in 3 variables. And he said that if the answer is yes, then the linearization problem in negative solution will have a negative solution for the affine 3 space in positive characteristic. And if the answer is no, then you clearly have a counterexample to this Zariski's cancellation problem for affine 3 space in positive characteristic. So either way, you will get to have you will be solving a one important problem in this area. Peter Russell used to call this dichotomy as asynchronous dilemma. I showed him that this ring A is not a polynomial ring when this integer m is greater than or equal to 4. For m equal to 1, and as a consequence, we solved this Zariski's cancellation problem does not hold for affine 3 space in positive characteristic. Uh, for m equal to 1, this is still not known whether A is a polynomial ring in 3 variables. And you never know that if you solve this for m equal to 1, that this is actually a polynomial ring, then you have a counterexample to the linearization problem in a negative, in positive characteristic. So the problem is still open for linearization problem. Now, I came to this asynchronous threefold. So as I said, this is still an open problem for linearization problem when m equal to 1. Now, let us look at this asynchronous threefold. There is a very special kind of polynomial in Z and T in 2 variables, as you can see, and with an important restriction that P does not divide S. So what is this bivariate polynomial? So what is so special about this? That is, we will come to know about when I study this epimorphism theorem. So the epimorphism theorem of Abhenker and Moe proves that if K is a field of characteristic 0, by the way, the statement of this theorem, one can explain it to any high school student also, but the proof also, the proof of this theorem, though run over 100 of pages originally, but they don't use any techniques or any higher mathematics for solving this. High school student also can go through the proof, though it runs over 100 of pages. So let K be a field of characteristic 0, and let f and g be two polynomials in one variable, be such that there is a polynomial in two variables p, such that if you substitute f and g in that polynomial p, you can get w. Then either the w degree of f will divide the w degree of g, or the w degree of g will divide w degree of f. So one of this case must hold. So clearly, if this degree f is 1, then this condition will be true. But it may so happen that both of these degrees are greater than 1, but still this condition is going to hold. This theorem, another version which we can state this theorem is in terms of commutative rings, is this, that if you have a surjection kzt from the polynomial ring in one variable with the kernel generated by a polynomial capital F, this is f and this f is different. So if the kernel is generated by capital F, then f is a variable in kzt, that you can replace z and t by kf. So the epimorphism problem for hyperplanes asks, so this theorem is for two variables. You can ask this similar kind of theorem in higher variables, that if suppose you have an epimorphism from a polynomial ring in n variable to a polynomial ring in n minus 1 variable with a kernel generated by one single element f, does this necessarily imply that f is a coordinate in this ring? That means whether you can replace f by one of this xi and by an automorphism. So as I said, this problem is known to have was proved to have an affirmative answer in the case positive characteristic 0 by Abhenker and Moe, and independently by Suzuki in 1975. Suzuki's method is a bit topological, and this was purely algebraic. However, it was known even before this landmark result that over a field of positive characteristic, this problem has a negative solution for n equal to 2. And later, Abhyankar and Sathe conjectured that the epimorphism problems for hyperplane will have affirmative solution over a field of characteristic 0. And this is an open problem. Till date, we have no example to counter example in characteristic 0. A polynomial f is said to be a non-trivial line if, because of this negative result, we have this definition. If kzt mod f is a polynomial ring in one variable, but f itself is not a variable in kzt. So such a f is called a non-trivial line. And an example due to Segre and later a family of examples given by Nagata is this bivariate polynomial, which you have seen in this asynchronous threefold. So this is an example of the small f is a non-trivial line in the polynomial ring kzt. So this is the speciality of this small f, that it's a non-trivial line. The epimorphism theorem problem for n equal to 3 in special cases have been answered by Sathe and Russell. So the special cases they considered when g is a linear polynomial in y, and Sathe proved it in the case characteristic 0, and later Russell extended it to any field. And in fact, their result was much more general. What they proved is that if this is G is an hyperplane, then you can change change of there exists a change of coordinates x1 and y1 such that this leading coefficient of y is a polynomial in just x1, and uh, in kxyz it's a g is a variable along with x1. So with a change of coordinate, you can write it as a polynomial in just one variable, and kxyz is a polynomial ring in one variable over kx1g. So we can ask this similar question in 4 variables. So suppose kxyzt mod g is k3, where g is a linear polynomial like this, and whether you can say that it's a polynomial ring over kx. So we have answered this problem for when ax is x to the power m and m is an integer greater than 1. So again, you can see this g will give rise to this threefold of the type which I have described in the introduction. This is the title of the talk. Now, let us study this threefold x to the power m y equal to fx z. So we begin with our background knowledge. So we have this asynchronous threefold, which is a example in this family. And what was so special about this? This polynomial in Z and T was a Nagata's non-trivial line in ZT. Later, Peter Russell, when I solved this, that this is not a polynomial ring for n equal to 3, Peter Russell asked me this question, that what if you replace this term by any non-trivial line in KZT? Say you consider this ring A. Is A still not a polynomial ring? So he asked me this question, but there is no classification known for non-trivial lines. There is a family of non-trivial lines given by Nagata, but there is no classification known for this, and it's an open problem that all such non-trivial lines will be among this Nagata's family. So one cannot attempt this problem by putting specific values to this fzt. Later, we also had this example of Russell and Chorus, and here again, it's an element of this family. But the difference is that this term also involves x, whereas this does not involve x. And then this is our complex number field, characteristic 0, and this is very much positive characteristic. So this led me to consider a more general threefold, a threefold of this type over any field, forget about the characteristic, and any polynomial fxzt. So why not develop a theory which will involve everything? And study for any polynomial fx zt, and so I investigated this threefold, and what were the kind of problems which were involved in this linearization problem or this affine fibration problem or this Riskis cancellation problem. The problem was to somehow determine a criterion for which this ring A is going to be a stably polynomial ring, or a criterion for which A is going to be a polynomial ring. This was there in this linearization problem or in the cancellation problem, and this was there in the affine fibration problem. And in the context of epimorphism theorem, epimorphism or this Abhyankar-Sartre's conjecture, when is if suppose this happens, A is a polynomial ring, when is this going to be a variable in kx, y, z, t? So this was the guiding questions when I study this threefold, to find criteria or necessary and sufficient conditions when these things will hold. And for that, the techniques which I used has come from this theory of GA actions. So this formulation of GA actions in terms of ring homomorphism, that is known as exponential map. So if you translate it in algebra geometry, what you will get is the group action of the additive group GA. So GA is nothing but the additive group K plus. So now I'm just defining you what is an exponential map on a ring A. So before that, is there any question so far? Hello? Is there any question?
I think there is none. You can proceed. You can see at the end of it.
Okay, so let me proceed. Now it becomes a little technical. So what is an exponential map? An exponential map on a ring A is a ring homomorphism from the ring A to the polynomial ring AU, satisfying the two axioms, which is that this composition A to AU and AU to A. So this is the natural projection map, U going to 0. So this composition is identity. So this is the first axiom of the group action. And the second axiom is this phi v composed phi u must be phi v plus u. So this is v, the action of u and action of v must be action of v plus u. You can read it like that, where phi v is this, I write underscore u to just denote this extra variable u. And this time it is phi v is extended. So you extend it to this ring AU to AVU by setting U to U. So you don't change U to U. So only thing you apply phi v. So if you look at this composition, this must be phi v plus U. For example, if you look at this ring KX, so from KX to KXU, be a K algebra homomorphism defined by phi xu to sending x to x plus u. Then one can see that this is an exponential map on Kx. So let us see some examples of invariants of GA action. So what is a ring of invariant? So ring of invariant is a set consisting of all those elements in the ring A which fixes A. That is phi of A is A, and one can see that this set forms a subring of A and it's denoted by A phi. It is an important subring of A. An exponential map phi is said to be non-trivial if this A phi is a proper subring of A. For example, this exponential map which I have discussed in the previous slide, that phi u of x is x plus u, the ring of invariant is nothing but the field K. There is no non-trivial polynomial which is fixed by this exponential map. In general, it is very difficult to classify all the exponential map of a ring, even if the ring A is a polynomial ring. The Dodson invariant of a ring A is a subring of A defined by the subring generated by all those polynomials f, where f is in A phi and phi is a non-trivial exponential map. So what we do is that we vary all exponential maps and look at the ring of invariant and consider the ring generated by all such ring of invariants. So again, it's a ring generated by all them. So it's a subring of A, and it is an important invariant of the ring. So by invariant, I mean that if we have any automorphism of the ring A to another ring B, the Dachshund invariant of A will go to the Dachshund invariant of B, or it is preserves under homomorphisms. For example, as I said, it's very difficult to classify all the exponential maps, and even for a polynomial ring Kn, one does not know what are all exponential maps. But we can show that the Dachshund invariant of the polynomial ring Kn is Kn if n is greater than 1. So proof is not so difficult. Let me give you a brief proof. In fact, this will be the only proof in the whole lecture. So let A be this polynomial ring in n variable, and I be any integer between 1 and n. And I define this exponential maps phi I from A to AU defined by phi I of xj to be xj. Means if I is not equal to j, I will fix xj. And if I is equal to j, that means phi I of xi is xi plus u. Then we can see it's an exponential map. And what is the ring of invariant of phi I? So it's fixing every other variable other than xi. So in this case, a phi I is x1, xi minus 1, xi plus 1 up to xn. Hence, if I take two such I, say I, that is why I'm taken n greater than 1. So if I take I equal to 1 and 2, I will see the ring generated by a phi 1 and a phi 2 is whole of A. So the Dachshund invariant is A. As an important corollary, what we obtained, which is very important here, that if A is an affine K algebra of transcendence degree greater than 1, and if the Dachshund invariant is a proper subring of A, then A is not a polynomial ring over K. So if in some case the Dachshund invariant is a proper subring and the transcendence degree is greater than 1, then A cannot be a polynomial ring over K. And this was something I used for this asynchronous threefold. So I in a general study of this threefold of this type, where I take G to be this denominator x to the power m y minus fx zt, and let small f denotes the image of capital F under the projection map x is equal to 0, and let small x y z t denote the images here, then the following are equivalent. So I proved an equivalence of 10 statements, which I will be listing one by one. So what I proved is that if A is a polynomial ring in three variables, if this ring happens to be a polynomial ring in three variables, this is same as asking whether A is a polynomial ring over the subring Kx. So small x is the image, and which is same as asking small f is a variable in kzt. So small f was the projection of a capital F for x is equal to 0, and which is same as saying that this g is a variable in this ring kxyzt, and if g is a coordinate, it will be coordinate along with x. So these two statements are also equivalent. If this is the g, then g is going to be coordinate along with x. And now I relate it with the Dachshund invariant of the ring A. So all these statements are equivalent to the fact that A is a stably polynomial ring, which was the case in the case of asynchronous threefold for some integer L greater than equal to 0, and the Dachshund invariant is whole of A. And this did not happen in this case of asynchronous threefold. And I showed this the Dachshund invariant of the asynchronous threefold is a proper subring of A. And so this is same as saying that if A is an A2 fibration over the polynomial ring Kx and the Dachshund invariant is whole of A, or if F is a line, if this is the case, and the Dachshund invariant is whole of A, so F is a line will not necessarily imply fzt is a variable, as there exist non-trivial lines in positive characteristic, but we don't have non-trivial lines in characteristic 0. So in characteristic 0, if this is the case and fzt is a line, that is always going to be a polynomial ring, and the Dachshund invariant is whole of A. And finally, the Dachshund invariant is whole of A, and This is a K theory K1 group uh, related to this ring A, and if the K1 group is K star, it's a trivial group, and A over K is geometrically factorial. So for simplicity, just assume that K is an algebraically closed field, then A is a UFD. And finally, the simplest condition which we can expect, that this ring has trivial units A mod xa. The units of this ring are trivial, and this ring A is a unique factorization domain. A is an unique factorization domain, and the Dixon invariant is whole of A. So all these later 5 conditions, they involve this Dixon invariant, and you see is this problem that this ring, whether it's a polynomial ring or not, is related to a, this is a polynomial in 4 variables, has been transferred to a problem in just 2 variables, that all you need to know is small f, not capital F. Whether small f is a variable, that is enough, and this criteria is well known. When is small f is a variable in KZT, this one can compute. Given f, one can compute whether that is a variable or not. As a consequence, now we see that for any field of any characteristic, and m is an integer which is greater than 1, this ring A is a polynomial ring in 3 variables if and only if this capital F0Z is a variable in KZT. So that means a problem has been reduced to this smaller problem, and now we can see why this threefold of Russell and Corus is not a trivial. This does not define the affine 3 space, because here fz is z square plus t cube. It's a cusp. It can never be a line. So this can never be a polynomial ring in 3 variables. This ring A is isomorphic to a polynomial ring in 3 variables, then it will be G is going to be a variable along with X. In some sense, it provides a partial answer to this Abhyankar-Satter's conjecture for the case n equal to 4, and analogy of Russell-Satter's theorem for the case n equal to 3. So Russell-Satter has a similar kind of result for n equal to 3. Now we have a solution to the case n equal to 4. Another important aspect of this is that this ring A is a polynomial ring in 3 variables if and only if it's a polynomial ring over Kx. So this Asanuma threefold, those three-folds can never be a polynomial ring, because Asanuma himself have shown that A is not a polynomial ring over Kx. Finally, this non-triviality of this A2 fibration over Kx, these examples will form non-trivial A2 fibration if and only if F0ZT is a non-trivial line. So as a consequence, we have answered this problem of three-folds, the problems second and third. And now I'm talking about the first problem. So given this ring A, the question is if F0ZT is a line, when is this a stably polynomial ring? So I proved that if F0Z is a line, then this ring A is going to be stably polynomial ring. So this problem of 4 variable is essentially focused on the problem of 2 variable. That if this is a line, then this ring A is going to be a stably polynomial ring. And we know that if it's a non-trivial line, then A cannot be a polynomial ring in 3 variables. Thus, whenever you have a non-trivial line, you give rise to a counterexample to the Zariski's cancellation problem for the case n equal to 3. But now I'm talking about K is a field of any characteristic. So there is no characteristic involved. But we know by epimorphism theorem of Abhyankar, Moe, and Suzuki that such non-trivial lines do not exist in characteristic 0. Hence, these kind of examples are not counterexamples in characteristic 0, though this proof is independent of characteristic. Another important feature which I discovered for this threefold was that if you see this threefold, they have 2 parameters. As I said, this is totally dependent on small f, where this is a polynomial in just 2 variables. So there are 2 parameters, this integer m and this small f. So let me denote it by m and f, where m is an integer greater than 1 and fz is any non-trivial line. Then what we showed is that two such threefolds are isomorphic if and only if this integer n is equal to n and f and g are equivalent. By equivalent, I mean that f is equal to some unit times g in the ring KZT. Thus, over a field of positive characteristic, if I vary my integer m and take any non-trivial line, I will get an infinite family of non-isomorphic rings, which are all stably isomorphic to the polynomial ring K. So this was the problem about the threefold in the affine fibration problem, linearization problem, and the cancellation problem. Now I will talk about the fourth problem, this Mianish's problem on GA action. So for that, let me introduce what is called a local important derivation. So it's the same as a derivation. So let K be a field of characteristic 0. This does make sense because though we can define it for any characteristic, but important results of this local important derivation do exist only in characteristic 0. So let A be a derivation is a K-linear map satisfying this Leibniz rule, and it's called a local important if for any element small a in A, there exists an integer na which depends only on the element A such that dn A is 0. So nth derivative of that element A is 0. So note that this GA is the additive group K plus, and when K is an algebraically closed field of characteristic 0 and A is a finitely generated K algebra, then there exists a one-to-one correspondence among a local important derivation, an exponential map, and the GA action on spec A. So local important derivation is same as an exponential map, which is same as a GA action when K is an algebraically closed field of characteristic 0. So all these concepts are same. So from an LND, we can define an exponential map, and from an exponential map, we can define an LND or a GA action. So all these concepts are equivalent. So an important problem, Miyanishi. So Miyanishi posed this problem. So the problem is for B is a polynomial ring in n variable and D be a non-zero k-linear local important derivation on B, and let A be the kernel of a derivation. So kernel means all those elements which are annihilated by D. It's a derivation, so A is the kernel of a local important derivation. So by general theory, it has been seen that this ring A shares similar property of the ring B. Though this is the unipotent group GA, the ring of invariant, this kernel need not be a finitely generated K algebra, but still this ring A enjoys several important properties of the ring B. For instance, this ring B is a UFD, then A is also an UFD, or like if you take a height 1 prime ideal here, that will remain an height 1 prime ideal here. So there are very close similarity between A and B, and seeing this similarity, Miyanishi says that it is expected that A enjoys to some extent several important properties of B. And then he asked a similar question. Say, for instance, we know because of Quillin and Suslin that all projective modules over B are necessarily free. So if B is a polynomial ring in n variable, then all projective modules over B are necessarily free. So are all projective modules over A necessarily free? Miyanishi asked this question in his survey article, which was published in a book. So he raised this question: are all projective modules over A necessarily free? Now we know by theorem of Ressler for the case n equal to 2 and Mianish's theorem for n equal to 3, the kernel A are polynomial ring, and hence the Quillin-Suslin theorem, Mianish's question has an affirmative solution for n equal to 2 and 3. So all these things were fine for n equal to 2 and 3. What if n equal to 4? Why I'm not asking about n greater than 5? Because if n is greater than equal to 5, the ring of invariant need not be even finitely generated. And it is not known, even for the case n equal to 4, whether the ring of invariant A is finitely generated or not. But in some cases, suppose we know this kernel A is finitely generated, can we still ask this question? are all, or a simple question or easier question, are all projective modules over A are stably free, at least stably free, if not free, at least are they stably free? So this stably free asks the questions about the Grothendieck group of the ring A. So this is the K naught group. So this is the problem for our all projective models over A are stably free, and we have answered this question to be a negative solution, and this has been answered in two steps. In the so the first step, what we do is that we constructed a ring and show that projective modules over this ring are not free, not even stably free. And in the second step, we show that such rings can be realized as a kernel of a non-zero local important derivation on the ring B. So we proved that if K is an algebraically closed field of characteristic 0 and Fzt is an irreducible polynomial, so recall again that this is the threefold of which has been discussed in the title. So we studied this ring A, and for Fzt being an irreducible polynomial and C be this curve where m is an integer greater than or equal to 1. So what we proved that if C is the coordinate ring of a non-singular rational curve, then the ring of this K naught group, this Grothendieck group of A is finitely generated. And if it is finitely generated, then it's not generated by just a Z, it's singly generated. So this was a statement of we proved that in particular, uh, if we, if I choose FZTB to be a non-singular curve, say for instance, if I take the cusp, which is a rational curve, then this Grothendieck group is not going to be finitely generated. In the next step, what we showed is that when K is an algebraically closed field of characteristic 0 and Fz is an irreducible polynomial and A is this ring, then A is isomorphic as in K algebra to kernel of D for some derivation in polynomial ring in 4 variable if and only if C is an K sub algebra of the polynomial ring KW. So when is this ring A isomorphic to the kernel of a local important derivation, and we have obtained this criteria that C must be a subalgebra of the polynomial ring KW. This has been obtained in a joint work with Bhattwadekar and Lokhande, Swapnil Lokhande. So and thus I have not written it down, but thus if you take C to be say the curve cusp, say T square T cube, then it satisfies this hypothesis. So A is isomorphic to the kernel of an local important derivation, and by this previous proposition, because it's a cusp, it's a singular curve, this Grothendieck group is not finitely generated, and thus we have answered this question of Miyanishi. We have in fact proved very much more general statement. We proved that forget about the projective models being stably free. We proved that even the Grothendieck group K naught of A is not finitely generated. That means what is a Grothendieck group? It captures the all stably free projective models, right? Means it's all stably free models. So the size of K naught of A is basically the size of non-isomorphic stably free models. Non-isomorphic stably non-stably isomorphic models. So even those K naught groups is not finitely generated. Thank you. So I end my talk here.
Thank you so much, Professor Neena, for such wonderful exposition of your famous work and the follow-up work after that. So let me first look at the audience. There is any question? I will move into the other part. So is there any question here in the from the audience? Here in the seminar room? Okay, so then doesn't seem like. We can move into the YouTube chat questions. Is there any?
There are no questions here in the YouTube channel also, sir.
There are no questions?
No, sir. No, there are no questions in the YouTube channel.
Yeah. So, thank you so much, Professor Neena. It was a wonderful talk, and we really got to know the work that that famous work, and it was really well explained. Even the open problems, there are many students here, and I'm sure they got benefited and Thank you so much. We hope
Thank
to
you,
see,
sir, for giving this opportunity. I will be looking forward to more such talks. Thank you, sir.
we hope to see you here at KSM, Neena.